Good. Yeah, me too. I got an 8-hour drive tonight ahead of me, so.
Where are you going?
I gotta go to Virginia for a family emergency, so I'm leaving, going home, picking my wife up, and we're driving until 2 a.m.
Oh boy.
Have fun with that.
Yep.
I highly suggest just taking the 981.
That's what I usually do. So my hometown's on 81, so
Oh, okay.
it's a straight shot for me. Yep.
Megan's like, let me tell you about my 14-hour drive today.
Yeah, 81's the secret for everyone running the Mid-Atlantic. Never take 95, always take 81.
The one time I took 80 or 95, I was stuck in traffic for hours.
Yeah, that's right. You get stuck in Philly and you get stuck in DC.
Yep.
And
Exactly.
And also down the George Washington too as well. So
I'm still trying to learn because I still kind of rely on GPS. So I'm still trying to learn how to kind of avoid the George Washington Bridge from coming back up here.
Right.
And try to just get on the Tappan Sea. And
that's right. That's the way I go, and I make it to Central Virginia in about 7 hours. That way. Of course, you have to drive like I do, which is 90 and a 70. But
basically, probably where you're ending, because you said about 7 hours, is where my halfway is.
yeah, that's probably right.
Like hour-wise.
That's right. Yeah.
Because I have to go through all the way.
Yeah, it's another 3 hours to the North Carolina border.
Yeah.
Yeah, so that sounds about right to me.
And then I learned North Carolina is about 2 hours for me.
Yeah.
And then it's an extra hour after that.
Right. Sounds about right to me. Okay, let's get started. Let me make sure I'm recording. I am, it looks like. So today we've been talking about entropy the last couple days, and today I want to give you what is my favorite definition of entropy. And so we've talked about the idea that entropy is the change in heat, reversible heat for a process divided by temperature, right? And this is a useful definition to do math, but it doesn't really give us a lot of physical interpretation, right? Other than that entropy is somehow related to heat change at a given temperature. And the question is what does this look like physically? Right? What is going on microscopically within a system that entropy correlates to, right? What is entropy measuring? And there's another formula for entropy that I haven't given yet, and I want to talk about that a little bit today. And it comes from, instead of a thermodynamic perspective, it's going to be a statistics and probability perspective, right? We're not going to do a lot of probability, but I think this gives us a really good physical sense of what entropy is, and it's really key, I think, to understanding what entropy is. And so there's an equation, Boltzmann, our friend Boltzmann, or my friend Boltzmann, during his PhD thesis came up with an equation for entropy. And he says that entropy for some system, S, is his constant, Boltzmann's constant. Remember that Boltzmann's constant times Avogadro's number is the gas constant, which is joules per mole per Kelvin. So the Boltzmann constant, just as a reminder, is the per molecule or per atom per particle gas constant. Right? It's a conversion. It converts energy into temperature, and the proportionality factor is Boltzmann's constant. So if you have a system at T, right, with some number of particles, then you can calculate the energy by multiplying by Boltzmann's constant. Right? And I'm sorry, I got one more thing here. And it's times this logarithm of this term W. All right, and we'll talk about what W is in a second. Right, so this gives us units of logarithms are unitless. Because this is a unitless number. And this is joules per Kelvin, right? Which gives us the right units for entropy, which are joules per Kelvin. All right, so what is this W? Boltzmann defines W as the total number of possible configurations for a system. All right, and I want to kind of give some examples of what I mean by this. We'll calculate W for some simple examples. In fact, on the problem set, problem 3 on the problem set, the final problem asks you to calculate entropy in this way by calculating this number of possible configurations. It walks you through that. And I kind of want to talk about the theory today about this. Right, so entropy somehow is, right, we often talk about entropy as a measure of disorder of your system. And we can kind of see that here, that the entropy is proportional to basically if the system, right, an ideal gas moves around randomly, right? Everything is random, right? And the more random or the more possible ways that you can randomly configure the system, the higher the entropy. Right? And so let's give an example. Well, let's first talk about how we calculate W. All right, so let's assume we have n molecules. And a system can be configured. All right, let me change that. And each molecule can exist in a finite number of states which we label, say, n sub 1, n sub 2, n sub 3, all the way n sub k, where n sub k is the number of molecules in state k. Right? We haven't defined what states are yet, but well, I'll give you a really great example in a minute. Okay, and what you can show is that W can be calculated with probability as the factorial n, I'll define what that is if you don't know what it is, divided by the factorials of all the possible configurations. So you take a product of all the factorials of the number of molecules in each state, and you divide the number of total molecules factorial by that. The definition of a factorial, if you haven't seen this in about 1 million years, that would be okay. Let me do it in a different color. N factorial is equal to n times n minus 1 times n minus 2 times all the way down to 1. All right, so for instance, 5 factorial is 5 times 4 times 3. And by definition, 0 factorial is 1. Okay, so that's the definition. So 0 factorial is 1. 1 factorial would also be 1 because it'd be 1 times itself. 2 factorial would be 2 times 1. 3 factorial is 2 times 2 times 1, and so on. Okay, so that's interesting. Right? This is basically the number of possible combinations of n particles in k different. Right? If you had n particles in k different boxes to put it in, the number of possible combinations of putting n particles in the k boxes is W. Right? So it's just a combinatorics problem. Right? But you can imagine this number must be huge. Right? Think about if this is 6 times 10 to the 23. Well, to calculate that would be impossible. Right? To calculate 6 times 10 to the minus 23 times that number minus 1, that times that number minus 2, all the way down to 1, we're talking about a massive number. The n factorial blows up. But there's a nice approximation. So I'm going to move over to the side of the board here. You can always there's what's called Stirling's rule, and I reintroduced this in the homework, which is that the logarithm of a factorial can be approximated as the number times the logarithm of the number minus the number. Okay, so instead of talking about factorials, we can think about logarithms of factorials, and we get this really nice approximation for it. All right, so remember that the logarithm of a number is the exponent of e that gives you that number. So this is the exponent of e when you take e to this, you get the natural log of n, right? So n factorial is equal to e to the minus n log n minus n, right? So you can imagine for 6 times 10 to the 23, you're taking a number that's on the order of 6 times 10 to the 20, e to the 6 times 10 to the 23. That's a big number, right? So we often don't work with logarithms. We work with natural logs of factorials. And that's really nice for us because, look, there's a logarithm of a factorial, right, in the equation for entropy. Right? So we can always write S as KB n log, or sorry, let me change that, W log W, or sorry, that's not right, excuse me, right? So if we plug in this number into here, so S equals KB log W, which is KB log n factorial over n1 factorial to nk factorial. And we can replace this with this. Let me split out remember that, let's use a couple of rules here. Log of A over B equals the log of A minus the log of B. And the log of A plus B, or A times B, is the log of A plus log of B. Right, that'll help us in this math a little bit. So this is KB log n factorial, brackets, minus the log of the denominator. Right, and then we can use Stirling's approximation to approximate these logarithms. Okay. All right, so entropy has something to do with the combinations of configurations for a system. So what I want to do is I'm going to give you a really simple example of this. All right, and we can actually calculate the entropy of this simple system. Just a little bit of work. So I'll go ahead and erase this. So let's, for instance, take a system. We have a box where you have some particles in it. It's just one big box. Volume V and n particles. Well, let's make it a real number. Let's do 100. 1,000 particles. Okay. 1,000 particles. And what we're going to do is we're going to change this box and quarter it into four smaller pieces, right? And we're going to let the gas diffuse around. And of course, what will happen is that you'll get n over 4 particles in each box. Right? That's what you would imagine that would happen on average, is that you would quarter the number of particles because you quarter the volume. So now the question is, what's the change in entropy when you do this? Well, let's think about what do we define as a state here. Right? We want to calculate W. We know n here is 1,000. But what is one n1, n2, and nk? Well, what we can do is we can let n sub j be the number of particles in box J. Right, so there's 4 boxes. Let's just number them A, B, C, D. Right, so the entropy of this system, let's just write W. W for this system is 1,000 factorial, right, n, divided by the number of particles in each box. Right, so that's 250 factorial times 250 factorial times 250 factorial times 250 factorial. Right, there's 250 molecules in each box. Okay, we'll come calculate this in a minute, right? So again, this is our initial state. And this is our final state. So what's W here? Well, W is easy to calculate. It's 1,000 factorial. And there's only one box. So W is 1,000 factorial divided by 1,000 factorial, which is just 1. Right, so that's easy enough to calculate. Right, there's only one box for everything to go in. So there's only one configuration. But notice this is, as we'll find out, this is much larger than 1. So let's calculate it. Let me simplify this a little bit. This is 1,000 factorial divided by 4 times 250 factorial. And let's take the logarithm and apply Stirling's rule to this. Right, so the log of W.
Wouldn't it be 250 to the 4th factorial?
Yeah, sorry, thank you. Sorry, my apologies. Right, thank you. Right, 250 to the 4th. So let's take the log of W, which is the log of 100 factorial, over the log over 250 factorial to the 4th. Right, we'll use log rules. This is equal to the log of 1,000 factorial minus 4 times the log of 250 factorial. I've used the power rule, right? When you take the log of a power, the power comes out as a coefficient. I'll just write that down in case you haven't seen that before in a long time. Log of a to the b is b times the log of a. Okay, so now we can apply Stirling's rule here. So the log of 1,000 factorial is equal to 1,000 times the log of 1,000 minus 1,000. And the log of 250 factorial is equal to 250 times the log of 250 minus 250. Someone have a calculator and can calculate these for me briefly? Let's do the 1,000 one first.
Yeah, 5,907.75.
5,907?
Yeah.
All right, let's just leave it there for now. And let's do the 250 one. Significant digits. We don't have to worry about too much here for this calculation.
1,130.
1,130. Okay. So that means then that the log of W for this system is going to be 5,907 minus 4 times 1130. Can someone calculate that for me? I could probably do it in my head, but
1387.
1387. Thank you. Yeah, it looked like something like that. So this, let's just look at this for a second, right? What does this mean? This means that W, the number of configurations for this system, the number of different ways to put 1,000 particles into 4 boxes, is e to the 1387. It's a huge number, right? So it's a massive number, right? You couldn't possibly calculate this yourself. That's why we use logarithms. Right, so you can imagine that this is a fairly random system, right? The number of possible ways it can arrange itself is this many, which is a big number. Right, so, but we can now plug that in and calculate the entropy of this system, right? So the entropy now is KB ln KB times 1387. And I have Boltzmann's constant. Just pull it up real quick. I think it's about 3 something times 10 to the minus 23. Yeah, sorry. So Boltzmann's constant is 1.38 roughly. Let's do one more significant digit. 1 times 10 to the minus 23rds joules per Kelvin times 1387. And I'll just calculate this real quick myself. So 1.38 1e minus 23 times 1387. So the amount of entropy this system has is, and the state is 1.91 times 10 to the minus 20 joules per Kelvin. And we can convert this to joules per mole on a molar basis by multiplying by Avogadro's number, which I'll do right now.
Can you explain what happens with the E for E though?
Here?
Yeah.
Well, okay, so the right, so the entropy is the log of W. So the log of W is 1387, which means W is e to the 1387.
Okay.
Right, so I'm just using the log,
Okay,
because that's what I need. And so this is roughly 11.53 kilojoules per mole per Kelvin. Okay? So the final state has this much entropy, right? And all entropy is just a measure of configurations, right? The more configurations, the more disordered the system is, the more ways you can arrange it, the higher the entropy will be. And the entropy here, in the initial state, is 0. Because W is 1, the log of 1 is 0, so entropy is 0. So by putting the box and subdividing it into 4 categories, I'm going to go ahead and erase this here. Right, delta S for this process is S final minus S initial, which is equal to 11.53 kilojoules per mole Kelvin minus 0 kilojoules per mole per Kelvin. That's the initial state. We're left with 11.53 kilojoules per mole. Do I have that off by an order of magnitude? Yeah, I think I do.
Did you directly multiply the 1.91 joules to the number because it's supposed to be converted to kilojoules?
I'm sorry, say that again.
Did you convert the 1.9 times 10 to the negative 20 to kilojoules before multiplying by Avogadro's number?
No, I did it first and then divided by 1,000. So let's hold on to that. I think I might be off by an order of magnitude, but let's calculate it a different way. So anyway, this is our number for entropy. And now let's go back to what we learned last class, which was that for at isothermal conditions, delta S is equal to NR times the logarithm of the final volume divided by the initial volume. Right? Remember, the amount of heat generated in an isothermal process is the opposite of the work divided by temperature. That's nRT times the natural log of the volume ratio. Entropy is the heat released divided by T, so you just lose the T here. Right, so let's just look at it on a molar basis. So R ln VF over VI, what is the ratio here? Well, we go from 1 to 4, right? So the ratio here is 4. R ln 4. Yeah, I'm off by some orders of magnitude. 8.314 times the log of 4. Yeah, I'm off by, sorry, this is wrong. This is joules. Sorry, I apologize. Yeah. And when you calculate this, guess what the value is? 11.53 joules per mole per Kelvin. Exact same answer. Right? So the idea is that entropy, all it is an energetic value that represents how much randomness and how much configurational variability there is in a system, which is really interesting. Right? There's a very famous theorist who worked at Bell Labs in New Jersey for a very long time, named Claude Shannon. He was very fundamental to computer science, and he came up with this idea of information entropy. The idea that in order to store information, you have to exert some amount of energy to store it. Right? There's some amount of energy per bit that you have to encode. And the idea is that the more bits that you encode to define a state, the more space you need and the more energy you need. Right? So imagine that each configuration you can write as a bit. And so in order to encode all the possible configurations of your system, you need e to the 1, for this system, you need e to the 1,387 bits. Right? And so in order to store that onto memory, you have to exert an equivalent amount of energy to store a 0 or 1 in a piece of memory, in a register on a memory. Right? So the idea of complexity, this idea of how many configurations you have, has a direct energetic component. Right? The system has to, in some way, randomly sample all of these configurations, and that requires a specific amount of energy, which is equal to the entropy. Right? So systems that have very low, where very ordered, right? Here we have particles sitting in one box. There's only one box to choose from, so there's only one configuration. They have very low entropy. But now when you split them into 4, they now have 4 boxes that they can sample, and your entropy jumps to 11.53 joules per mole Kelvin. Right? And it doesn't matter if we approach this from an information standpoint, right, a probability standpoint, or from thermodynamics, we get the exact same answer. They're exactly equivalent. So this idea is that entropy is an energetic measure of the complexity of a system as it samples its state space, right? The number of possible states. Right, so the more complex the system is, the more places it can sample, the higher your entropy is going to be. Any questions about this so far? Okay. So the problem on the exam, there's a problem, not the exam, sorry. On the problem set is very similar to this. What you're doing is you're partitioning, in that problem you partition the box into 2. And what we look at is, the idea is the assumption we've made here is that when you split the box into 4, that the particles distribute equally into each box. But there's a very reasonable assumption to say, well, if it's all random, there might be a probability where you have 3 of the boxes filled, and no particles in B, right? That's a perfectly reasonable way for the system to arrange itself. And I asked you to calculate what's the probability or what's the ratio of state configurations where the box is equally distributed versus ones where there's a deviation from this equilibrium value. And you'll find that as n grows, as the number of particles grow, the amount of configurations where there's a non-equal distribution becomes diminishingly small, incredibly small. So small that you can't even calculate W for them. Once you get to about 10,000 particles, once you get to about 10 or 100,000 particles, W becomes so large that you can't actually calculate it. And the probability of seeing a deviation like this, where only one of the boxes is empty and 3 of them are filled, is so small that you would never see it, right? Over the course of a mole of universe lifetimes, you still wouldn't see it, right? It's a vanishingly small number. So what this proves is that this idea that if your n is large enough, the system will almost always, to any physical realization, to any physical probability, physically realizable probability, will expand in this way where everything is equally filled. Right? The exact idea that it just splits into half or into quarters. And so once you get to a mole of particles, there's basically never a chance for you to ever see anything other than this. The amount of configurations where the deviations are large are so vanishingly small, it's impossible. Right? And so this, in some ways, this proves thermodynamics, right? The assumption that we make thermodynamically is the system is random, and so everything's randomized, that over time the system should exhibit this distribution where everything's equally filled. And that's the assumption of thermodynamics, this idea of thermodynamic equilibrium. And so what you show is that as n gets bigger and bigger, as you get to macroscopic scale, bulk scale, that thermodynamic equilibrium is the only probable way for the system to distribute itself. Right? Entropy enforces that. Right? Entropy says, and the important thing is that a system will always evolve to maximize its entropy. I often like to say that thermodynamic systems are lazy. They like to minimize their energy, as we'll see when we get to Gibbs free energy next week. We'll talk about Gibbs free energy, delta G, right? A system wants to be at the lowest possible delta G, the lowest possible energy, and also wants to have maximum entropy. So it wants to exhibit the least amount of, it wants to be at the lowest energy state, and also make sure that its bedroom is as messy as possible, right? Which is the maximizing its entropy, right? So thermodynamics is literally a lazy theory. That all systems thermodynamically will evolve to the lowest energy form with the maximum possible disorder, right? And in some ways, the principle is that physical processes want to exert the least amount of energy possible, the most efficient way from point A to point B. And that means that you have maximum entropy. Okay? And that guarantees, again, this is the maximum entropy configuration for 4 boxes. Right? This has higher entropy than, say, if this were 0 and the other ones were n/3. We can calculate it, that has lower entropy. So that state is very unlikely. So over an infinite amount of time, the system will always evolve to having all the boxes equally filled. Okay? Entropy enforces that. More importantly, is that not only does entropy enforce that, it also enforces that going backwards is impossible. Right? This process, delta S is less than 0, which means that it requires external energy to complete. Right? You have to get in there and move all the particles and move everything around so that you get this system back again. Right? You have to put energy into the system. Right? It's the same idea as when we talk about a sand on a plate. You know, in order to reorganize a shaken plate of sand, you have to put energy yourself into reorganizing it. Right? That entropy will always allow it to become maximally disordered. And so for you to force it backwards, you have to put work into the system to do so. Okay. I want to stick on this topic for a minute and look at something a little different. I want to come back to this idea of, just to reiterate that this idea of entropy goes right back to what we learned about ideal gases and thermodynamic equilibrium. What we're going to do is we're going to take this idea that entropy is proportional to W, this configuration, number of configurations, and show that you get the same probability distribution for energy that we saw with the ideal gas, the Boltzmann distribution. So just a very simple derivation. Right? And this will complete everything, right? That a system, the idea that a system is at thermodynamic equilibrium, thermodynamic system, means that it has maximal entropy. It's something that you can very easily prove. What I want to do, I'll leave this point up here, it's important, is I want to consider a system. Doesn't matter what system we have. But let's consider a gas. With n sub 0 molecules in the ground state. I'll tell you what this means in a second. And n sub j molecules in the jth state. What I'm going to assume, and this is something that we're going to learn next semester, is that molecules don't exhibit a continuous distribution of energies, but rather a discrete one. There's different types. Let's look at molecules, for instance. Molecules have different types of motion. They have translational motion, right? X, Y, Z. Rotational motion, and vibrational motion. We'll ignore electronic for now. they have three different kinds of motion. Right? Vibrate. The bonds can vibrate. The whole system can rotate, and the system can move around in space in x, y, and z. I'll plot this versus energy. And what you can show is that a single molecule, can't exhibit any translational energy at once, but at discrete steps. So the energy spectrum looks like this. So it's very finely spaced, so I'll just put a bunch of states here. Right, so the system can only exist at these discrete energies. And the rotations are a little wider. And the vibrations are even more wider. Like that. Let's just say they look like that for now. Okay, so the molecule, let's say for instance, we name the energies of each of these states, like say epsilon naught. This is the zero translational state, 1, 2, 3, right? As you increase the kinetic energy of the system, E sub 1, E sub 2, E sub 3, and so on. All right, so let's imagine that our system be at a temperature T. Okay, which means that there's an average amount of energy available to the system to use, which I'll draw by here, which is equivalent to kBT, or RT. That's the amount of energy available thermally. Right, so if this is all the system, the molecules have in energy, then they can sit in any number one of these states, right? So if you have many molecules, maybe this state has n sub 0 molecules, and this state has n sub j molecules, right? You have many different molecules. There might be some in this state, some in this state. Maybe there's some in this state for rotation, some states in here for vibration, and so on and so forth. Okay. But the idea is that we can ask every molecule in our sample, which one of these states are you in? And we just count them. So n sub 0 are the number of, for instance, in this case, n sub 0 is the number of molecules that have no kinetic energy, right, that are just standing still. Right, n sub j are the ones that have this much kinetic energy, right, the number. Okay. So what we're going to do is we're going to assume constant volume. So work, PdV, which is work, is 0. Right? So all the energy is heat. So by the first law, U is equal, du is equal to dq. Right? And of course, by the second law, the change in entropy is equal to dq, the change in heat divided by temperature, which is the change in energy divided by temperature. Right? The change in total energy divided by temperature, because there's no work. Okay, so now let's imagine the energy difference between n sub 0 and n sub j states. Right? And so let's imagine we excite a molecule from the lower state to the upper state, right, which has an energy difference, would be E sub j minus E sub 0 minus T. Right? So that's the entropy change by taking a molecule from the ground state and exciting it up to the j state. Would be the energy difference divided by the temperature at constant volume. So now let's let the number of molecules in the ground state and the number of molecules in the excited state to be much big, right? Big numbers, much greater than 1. So now what we can do is show that also that, right, so ds is equal to this, but we can also show that ds is equal to kb ln w final minus kb ln w initial w final here is going to be, let's say there are n total molecules in the system. Okay, so w final is n factorial. And then again, there's going to be n0 particles in the zero state, n sub 1 particles in the first state, the first excited state, all the way up to j, and so on, right? There's also n sub j plus 1. It just keeps going. Right, so we have a big number under there. This is the initial. Sorry, this is the initial. And then what we're going to do in the final is we're going to take a particle out of the ground state and excite it. Right, so in the final state, the new n sub 0 is going to be n sub 0 minus 1, and n sub j is equal to n sub j plus 1. Right? We remove a molecule from the ground state and we add it to the excited state. So the W final is equal to n factorial divided by n naught minus 1 factorial, n1 factorial, all the way to nj plus 1 plus u factorial, and so on. Right? We've removed one from the ground state and put one in the excited state. So now we can calculate the difference in entropy about this change. So the change in entropy, we'll say delta S is equal to KB ln W final minus KB times the log of W initial. Okay, and I'm not going to go through the math here, but you can do a little bit of algebra here. If you use the log rule that ln A minus ln B is ln A over B, and then apply, and then take the ratio of these two, you find that what you get is KB log n sub j factorial over n sub j plus 1 factorial times n sub 0 factorial over n0 minus 1 factorial. Right? All the other terms cancel out, right? n1, n2, n3, all of those are exactly the same, so they cancel out the denominators when you take the ratio, and the n factorials go away too. Right? So you're only left with the ones that change. And once you do this math, you find that this is KB ln n sub 0 over n sub j. Okay, so delta S is equal to the Boltzmann's constant times the log of the ratio of particles in the ground state versus the excited state. Right, that's delta S. We also have a value for delta S here, the energy difference divided by the temperature. So we can equate them. We have E sub j, which is the energy of the j state, minus E sub 0, the energy of the ground state, divided by temperature, is equal to KB ln n naught over n sub j. And then once you solve for the ratio of the particles, you find that the ratio of the particles in the excited state divided by the ground state is equal to e to the minus delta energy over kBt. Or this is delta epsilon, change in energy by temperature. We've seen this equation before. This is the Boltzmann equation. Right? When we calculated for an ideal gas, we assumed that the particle's energy is just kinetic energy, and that the probability of finding a particle at a given kinetic energy is proportional to exactly this. Right? That's what we assumed when the system was random and was moving randomly. That the probability of finding a particle in a given position or given energy or given velocity is proportional to e to the minus difference in energy divided by kT. This is the ideal gas Boltzmann's distribution. Sorry, this is distribution. Right? That was what we assumed for randomness. Right? So this comes down again. This connects this idea of a system's randomness being associated with entropy. Right? By assuming entropy, we get the probability distribution of our system back. Right? Of a random system. This is how we calculate the probability or the distribution of particles in a given state. This Boltzmann distribution. That's how we did it for the ideal gas. Or we could go from here and go backwards and get entropy. Right? So the idea is that entropy is an energetic encoding of the randomness of a system. Notice that this makes a lot of sense. Because if you're at a given temperature, this is how much energy the system has. Obviously, a molecule can't be above here because there's not enough energy for that molecule to have that much. Right? It can't be up here. It can only be here. So how many different states can the molecules be in? Well, it can be in any of these, right? These are the accessible states. But as we increase temperature, maybe we increase temperature here. Now there's all these extra states the molecules can be in. Right? Every molecule has this much energy available to it per mole. So as we increase the temperature, the number of states that it can be in increase. Right? So for this kind of example, that means that entropy is proportional to temperature. Right? The more energy you have in your system, the more available states there are. And therefore, the more random the system is, because there's more places the system can arrange itself into. There's more combinations. And instead of having just 10 available translational states, you now have 20. And so now you have a factor of 20 factorial in the denominator instead of 10 factorial. And so the system becomes more random and entropy increases. Okay, so entropy in some ways is just a count. It's just an energetic count of how many states the system has available to itself to sample. Right? Of course, the sampling is random. The system can be on average in any of these states, but because it's random and there's a probability distribution, and it's proportional to the temperature. Right? Higher the temperature, the more likely it is to find the system in higher states in energy. And as the temperature goes down, the less likely it is to find it in higher energy states, of course. And that would mean that because there's less available states, there's less configurations, and so the entropy decreases. Right, so entropy in some ways is a way to count states in a system. Right? The more states a system has, the more ways it can configure itself, the higher the entropy. And that complexity has an energy associated with it, which is entropy. Okay, so this is a very, very, very powerful way to analyze it, with this idea that molecules or atoms can only exist in discrete states, right? That we can assign a ground state for translation, or a first excited state, or a second excited state. Kind of like how we do it for the hydrogen atom and its energy levels. Right? And when we do quantum mechanics next semester, we'll realize that this is precisely true. The amazing thing about this, right? So Boltzmann, this was the 1860s, 1840s, 1850s. Boltzmann had this brilliant idea to say that a particle can't exist in a continuum of states, right? Right? The assumption was that a particle can be in any energy between these two numbers. But what Boltzmann assumes is that you can't do that. Boltzmann says that the states are what we call quantized, right? That we can index them with an integer, 0, 1, 2, 3, 4, 5, 6. And from that assumption, he comes up with all of this idea about entropy, and he's exactly right. So he comes with the realization that systems don't exhibit a continuum of energies, but rather a system of quantized or discrete states of energy. And he realizes this and comes up with this entropy concept 50 years before the idea that the proof that the states were quantized ever existed. This is quantum mechanics. Right? This was discovered by Bohr and Heisenberg and Schrodinger and all those guys from the 1920s. You know, at the advent of quantum mechanics, they actually proved that molecules and atoms and particles exhibit this discrete spectrum of energies. But Boltzmann showed that the only way you can do thermodynamics is by assuming this. And of course, people thought Boltzmann was insane, because at the time, no one had any clue that this was the real thing. This is what actually physics looks like at a microscopic scale. And they thought he was nuts. Now, Boltzmann was actually a little nuts in real life. but sometimes insanity is what brings genius. And so Boltzmann predicted this idea of quantum mechanics half a century before it actually ever existed. Right? And what he does is he says that you get thermodynamics back when you assume that the number of particles in your system is very large. So when you assume that the particles there's a lot of particles and the volume is very large for your system, then the spacing between the energy levels gets very small. So we can treat it as if it were a continuum, right? That you can't tell them apart. They're just all stacked on top of each other. But the key understanding is that these energy levels are quantized, like so. A system can't exist in between an energy, right? It can't exist here. It can only exist here and here. Right? And that's the whole reason. Without that, we would never be able to come up with any of this idea of entropy. Entropy is, in some ways, is intricately connected to the idea of quantum mechanics. This idea of particles being discrete and energy being discrete. I'm jumping ahead a little bit on that. But it's an interesting point. And it was really amazing that he came up with this without having any experimental validation of any of these microscopic concepts, right? He had no concept of this. He just guessed. I mean, he literally just guessed. I mean, he had a good guess, but it's a guess all the same. He has no experimental evidence to suggest otherwise. He later finds experimental evidence to prove these things, but at the time it was just a guess. Any questions about this? Okay, we'll come back to this concept later. What I wanted to get at is, again, that we can talk about entropy in terms of heat transfer, right? A thermodynamic concept, right? We can measure a heat transfer in and out of a system, and we get the correct value for entropy that we get when we take a microscopic approach, right? That's really the power of Boltzmann's insight, is that we can look at a system microscopically like this, or we can look at it in a macroscopic way by measuring heat. And the only difference between these two methods, these two analyses, are perfectly valid and give you the same answer as we showed, as long as you assume that the number of particles is very high, right? That the number of particles is much, much greater than 1. Interestingly, this distinction starts to break down when you get to very low temperatures or very low particle numbers. Things get weird. But we're not dealing with that. That's a later concept. But if you're thinking about things in the bulk, right, things at a molar scale, it doesn't matter if you look at this in a microscopic way or a macroscopic way. You get the same answer both, no matter what. Okay. Right, so what time is it? We got 15 minutes left. Yeah, so I want to do, this is kind of a math heavy lecture. I want to look at one more thing. And this is a little bit of an advanced topic, and it just reiterates the beauty of Boltzmann's insight. Something very beautiful about it, I think. So again, what we showed is that the probability of finding a particle at energy E sub j, and we call this probability P of E sub j. My marker's starting to die. So this probability of at E sub j is proportional to e to the minus E sub j over kBt. Okay, that's what Boltzmann says. Right, and so we could say then we can also say that the probability is actually equal to e to the minus E sub j over kt times a constant 1 over q, where when you apply this and take the integral over all the probabilities, you sum over the probabilities, integrate by energy, from 0 to infinity, right? You ask the question, what's the probability of finding a particle at any energy, which is all this is asking, is 1, right? And Q is called, this normalization constant is called the partition function. And it roughly measures number of available states at a given temperature. So it's just a normalization constant so that when you integrate, you get 1 back, right? That was something that we did with velocity, right? We said we pick a particle, an ideal particle out of an ideal gas, ask its velocity, what's the probability of it getting a specific velocity? And we know that if we ask all particles what their velocity is, that the total probability has to be 1 to find any particle at any velocity. All right, so Q is the factor that allows us to integrate, to normalize this integral to 1. And we call that the partition function. So what Boltzmann shows is that entropy can be described as the sum over all the states of the probabilities to find the states times the change in the probability, infinitesimal change in the probability. So probability times the differential in probability. So you can integrate both sides of this and get delta S. This would give you delta S if you integrate both sides. Right, you're integrating the probability distribution with respect to itself over all space, and you get the total entropy change of the system. But let's just look at it as a sum for a second. And then what we want to do is we want to put a little heat into our system. So let's let S go to S plus ds, right? We're going to put a little bit of entropy in the system. Right? We're going to mix things up a little bit. And what you find is that ds is equal to minus kb times the sum over all the states of the change in the probability plus the log of the probability at a given energy times the change in that probability. All right, so this is just a little bit of calculus. But we'll see how this simplifies, so just bear with me. This is just a little bit of algebra. And I can split this up a little bit to simplify it and write this as kb times the sum over all the states and how the probability changes, right? dp, right? That's a small little change in the probability times the log of the probability times the change in the probability. All right, so I just split it up and added the signs to both. We can rewrite this as negative kb times the change in the sum of all the probabilities. All right, how does the sum change of all the probabilities times this term? We'll come back to that term in a second. But this is 1, right? If you sum up over all the probabilities of finding all the particles in any energy, which is what this is saying, what's the probability of finding a particle at any energy? Well, that's 1. The derivative of 1 is 0. So this is kb times the derivative of 1 plus this term over here. And this is 0. Right, so this term goes away. And what we're left with is that the change in entropy is equal to kb times the sum over all the states of the log of the probability times the change in the probability, the differential element of the probability. And now we can plug in our probability function here. And this is equal to minus kb times the sum over all the states of minus 1 over kbt. I'm just taking the log of that exponential function up there, minus the log of q, the denominator, the partition function, times the change in the energy, the probability. This is just a number, so this goes away. And what we're left with is minus KB times the sum of minus 1 over KBT. Oh, sorry, E sub j, sorry. Right, you sum over the energies times the sum of the change in the probabilities, but we just showed that this is 0. Right, so this goes away. So what you're left with is that the change in entropy, well, this is kind of a complicated math equation, is 1 over the temperature times the energy times the way the probability changes as you introduce heat into the system. Let me write this over here. So what we're left with after all of that math is that ds has a 1 over t factor. And what we're going to do is we're going to sum over all the energies times the probability of seeing that energy, or times the change in that. Right? And then we also know, though, that ds is equal to dq over t. So that means that the change in heat is a weighted sum of the energies times how the probability of that finding a particle with that energy changes as you change the heat. So what this means is that the entropy change in a system is just the sum of the different state energies times how the probability of finding a particle in that state changes as you input heat into the system. Now, I know this is complicated, but what I want to say is that nothing to the system is changing. But what this means is that when you change entropy, what you're doing is you're changing the probability of finding a particle or the number of particles at a given energy. Right? So as you start to heat a system up, or as you start to put entropy into the system, what that means is that the occupation numbers, right, how many particles might be in a given energy level, changes. And so as it changes, the energy of the system changes, the total energy, the weighted energy of the system changes, and so the entropy changes, right? So all entropy measures, a change in entropy measures, is just how the system distributes itself amongst all the possible configurations. So this is just a really long way to say, I'm going to go ahead and erase this math here. This is just a long and complex calculus way of saying that entropy, that changes in entropy, are changes in the ways a system can arrange itself. So if entropy is negative, if we order a system, that means there's less combinations for the system to fall into, right? There's less arrangements. W gets smaller. And as entropy increases, that means that there are more possible places for the system to arrange itself, right? And we saw this here, right? As we increase the temperature, more states become available for the molecules to exist in, right? And so that's all that means. Entropy just changes the probability of each particle, the probability of finding a particle in a given state. Right? Each state has, this state has energy Ej and Nj, and if we start to increase the heat of the system, Ej is, of course, always the same, but Nj changes. The probability of finding a particle in that state changes. Right? And that's all entropy is. Entropy is just how the system rearranges itself. And there's an energetic cost to that, right? You can imagine that if you take a box and you partition it into 4, you can show that the enthalpy does not change. So the enthalpy change from going from 1 box to 4 is 0. The system doesn't transfer any heat in and out of the box. But there is an energetic component. There's an energetic change because you're taking a system from 1 box, 1 arrangement, into 4 boxes, right? And that has a definite energy change. So by doing that, the system rearranges itself, and that exhibits an energy change. There's no energy being created, right? If the box is isolated from the surrounding environments, it's not that it's magically creating energy to do this. All it's doing is rearranging the available energy into the of the system, the entropy of the system, into a new arrangement. Right? What this means is that another important thing is that entropy measures the amount of heat or energy available in a system, or sorry, not available in a system for a meaningful process. So if we have a box at temperature T, and we partitioned it into 4 boxes, right? This box always has this residual energy, right? RT. Right? So our box at 300 Kelvin has this much energy. We don't know what that energy is doing, but there's energy. There's some kinetic, some entropy. And we rearrange the box into 4. We partition the box into quarters. Some of this energy has to be used to move the system into the 4 boxes. So some of this thermal energy that's available is being reserved for the entropic change from when you go from 1 box to 4 box. You can't avoid that. That always happens, right? This rearrangement, entropy in some ways, changes in entropy is energy reserved only for reordering or rearranging a system. It's energy that, to our eyes, right, as we're someone who wants to exploit a system to give us energy for a process, is just thrown away. We can't do anything with it because the system needs it to rearrange the probability of all its particles and adjust them in their energies as you change the energy in the system. Right? It's just a change in probability and a change of the way that the system arranges itself. You can't do anything about it. The system will always do that, and that energy is just thrown away. It's not being thrown away. You have to have it. It's just not useful information. It's not useful energy. Right? So any process that you go through has this entropy change, which is the system reserving for itself to change its configurations. So what we're gonna have to start thinking about now, next week, is let's say that we have a process that has enthalpy delta H. Okay. Right? We know that this is heat released from the system, right? This is heat transferred in and out. Right? This is energy that we can use. And we know that the total energy delta U minus delta H is not equal to 0. Right? We showed that a couple days ago. We had a couple examples. One was with the hydrogen fuel cell reaction. We take H2 and O2 gas to convert to H2O liquid. We showed that this difference between the total energy change and the enthalpy change is large. And then we did it for calcite and aragonite, right? You go from one crystal to another, and this difference is very small. And the question is, what is that difference? What we're going to find is that this difference is proportional to the change in entropy, right? It's how much energy, how much heat is being reserved for rearranging a system to the new place, into the new to the new arrangement of the system, and that energy is reserved. So in order for a process to go to completion, it's going to either absorb or release some useful heat, which is the enthalpy. And there's going to be a little bit of extra energy that it also changes, or either absorbs or releases, that gets devoted to internal processes, right? Internal rearrangement of the system, delta S. Right, so delta S so if there was no entropy, we would always get out as usable heat in a constant pressure system, delta U. This difference would be 0. But because there is entropy, and entropy always needs to be a maximum and is always increasing, we're never going to get all the possible energy out of the system from its process because some of it's going to be reserved for entropy. And so what we're going to think about, and very soon, is the idea of, well, it's unfortunate that we can't use this energy for anything, but maybe we need to instead think about analysis of a process by thinking about how much energy is left over to be used after we consider delta S. Right? So we know we're going to lose some energy to entropy, and what's left over? So the question I'm asking then is, what is delta H minus the energy content of delta S? Which again, because this has units of joules over Kelvin, we need to multiply it by temperature. What is the remaining energy available? Right? So delta H, for instance, is the amount of heat that's transferred, and we're going to lose some energy because of delta S. So what's left over? Exactly. This is Gibbs free energy. All right, so I don't want to start Gibbs free energy today. We'll start it next week. But this gets to the point of Gibbs. Right? We're also learning about Helmholtz, which is also similar. The idea is that any process is going to give you some useful heat. It's going to give you some useful energy, but some of the energy is always reserved for entropy. And the question is for a process, is there any heat left over for us to use? And we're going to come to Gibbs free energy with that as our answer, right? Delta H minus T delta S. Okay, so that's all I have for you today. That'll be it for entropy. We'll talk a little bit more about entropy in the context of free energy very soon, which will get us into the third law. And then we're going to dig into Gibbs. And we'll realize that Gibbs is amazing. It's an overpowered tool. And it's the only thing we'll ever want to use most of the time. So we do a lot of delta G from here on out.
Is it the press triangle to win?
I'm sorry?
Is